Hello everyone, welcome to the high energy seminar. So today we are very happy to have Algebra.
It's great to speak here at the high energy theory seminar. The topic of my talk is going to be algebra of infrared, and a particular generalization of it in a particular direction. So the task ahead of me is kind of difficult because this first four letters, algebra of infrared, is the paper that was written maybe nearly a decade ago now. In fact, here at the Institute was, I think, probably one of the longest papers in high energy theory at the time. So, and I'm going to be talking about a generalization of that. So let's see how far I get in an hour. Okay, so let me begin. So the common theme of the talk is going to be the category of boundary conditions in a two-dimensional quantum field theory with some kind of topological symmetry. And an equivalent way of, we don't necessarily have to talk about topological quantum field theory, but we can instead talk about supersymmetric boundary conditions in a supersymmetric field theory. And if there's enough supersymmetry, we can go between the two concepts by this notion of twisting. And so the general statement, which we'll use again and again in this talk, is that the boundary conditions of a two-dimensional TQFT organize itself into an A-infinity category. So I will explain what these words mean. So let me just give the definition first. So an A-infinity category consists of a collection of objects written as B for boundary condition. So for each pair, B prime, there is a Z-graded vector space written B prime. So this is graded by the ghost number, quote unquote. And then so there's a vector space for each pair, and then there's a composition map MN, which gives an n-ary map from tensor product of n of these spaces to a single one. And this has a certain degree. And these collection of maps satisfy a set of quadratic equations known as the A-infinity equations. And so what you should really think about is that this is a generalization of the case of an ordinary category where the only composition is M2. So that's just the ordinary composition in the category. And then this equation here just collapses to the associativity equation for that map. So this is a generalization of the notion of an ordinary C-linear category. Yes.
Is there a more physical way to describe it? Say it's operator that change the boundary condition.
Yeah, exactly. That's right. So yeah, this is just a map definition, but physically I'll get to that in a bit. B prime is exactly supposed to be the space of local operators at a junction of two boundary conditions. And this is some kind of these MNs are some kind of OPEs of these operators. And so just to unpack this a little bit, we have M1, which is just a map from B1, B2 to B1, B2. So this is just the ghost number one map, which squares to 0. Physically, you should think of this as a BRST operator. And M2 is an ordinary composition, and D and M2 are compatible in the sense that they satisfy Leibniz rule. M3 gives a chain homotopy between the two sides of the associativity equation and so on. And so if I take cohomology with respect to D, I just get an ordinary C-linear category in which the composition is associative.
Can you explain why M2 is squares to 0?
M1 squares to 0.
Sorry, M1.
Yeah, so if you just look at this equation, the simplest version of this equation is just M1 composed M1 is 0. There's nothing more to it.
But if I think of it as an operator that maps the boundary conditions.
Yes. So it's just saying what this is saying is that there is some BRST operator in the theory.
Which you're calling M1.
Which I'm calling M1, yeah.
Which is what?
Which I'm calling M1. So there's just something that maps an operator to itself. Ghost number one.
The higher MNs are more or less the product of N operators.
Yes.
Integrated over appropriate multiples.
Yes, that's right. Yes. Yes, and so, okay, yeah, if I take cohomology, I get an ordinary C-linear category. And usually, this is the thing that people explain by drawing sort of standard pictures in 2D QFT. So as and Nadi was asking, here in this standard picture, we have objects or boundary conditions of this category. Morphisms are operators at a junction, and products are given by taking the topological OPE of boundary operators. And so instead of going through these pictures, which I believe I have done in previous talks, I'll just explain how some of this works in a quick example. So this example will not be my main interest. I'm interested in, as I said, algebra of the infrared, but this still helps me illustrate some things I'll use later. So the example I'm going to talk about for now is going to be the two-dimensional topological BF theory. So if I have G to be a Lie algebra, I take V to be a scalar field value in the dual of the Lie algebra and A to be a one form. And the 2D BF theory has this standard BF action where F is the two form, and you can write this as a free part plus an interacting part. Interacting part from all destructive constants. And we're interested in boundary conditions, so we can formulate this on a manifold of the boundary. And so there are two standard boundary conditions. The first one involves setting B to 0 at the boundary with A free. I call this Dirichlet. And then the opposite one, where A is set to 0, B is free, and I call that Neumann. And my terminology is actually opposite to the standard one used in gauge theory. But it's justified if I think of this 2D BF theory as a Poisson sigma model into the dual of B algebra. So there, the sigma model field is actually B. And so if I set that to 0 from that sigma model perspective, it's actually justified to call it Dirichlet. So these are the two standard boundary conditions.
Sorry for being.
Yeah.
Well, since B and A are kind of consumer pudding, maybe not in two dimension, because one is a scalar and the other is a gauge field. If you make them arbitrary high-form gauge fields in any dimensions, they are on. It's clear that directly for one is normal for the other, and there's no preferred choice.
Mm-hmm. Well, I mean, I still have to choose which one I'm setting to 0. So it's just.
I don't think Ahsan's claiming it can be preferred choice. He's going to discuss both choices.
No, but he said that it's different than the standard choice.
No, I'm just talking about terminology. My terminology is, yeah, just the name. So usually people in the gauge theory, if we say A is equal to 0, it's called Dirichlet boundary conditions for the gauge field. So I'm just clarifying that. Yeah, okay. So let me first discuss the subcategory of Dirichlet type boundary conditions. And so I want to discuss HOM-DD, space of local operators that survive at the boundary for a Dirichlet boundary condition. In other words, remember to see it, yeah, in the Dirichlet boundary condition, B is set to 0 and A is free. And so the way I will do this is by using the BV formalism, where I extend the field space in this way. So B gets extended to have a one form and a two form part, and A gets extended to have a 0 form and a 2 form part. So these are the various fields in the BV complex. This is the ghost. B1 is the antifield of A. B2 is the antifield of C. And A1 is the antifield of B.
Also called the anti-ghost.
Yeah, anti-ghost. And so the BV bracket is just says that the pairing of B with A is given by wedging and integrating, etc. And so the BV action is just the same, essentially the same action with these curly versions of the B's and the A's. And in ghost number 0, it gives the previous BF action. And so the souped up version of Dirichlet just says that curly B vanishes at the boundary. So what therefore survives is this thing. So the free part of the BV BRSD differential is just given by the Deron operator. And so in particular, Q free acting on the ghost is 0 and Q free acting on the gauge field is BC. So in the free approximation, we see that the local operators that survive on the Dirichlet boundary condition just consists of C and its products, but not its derivatives. The derivatives are Q exact. So we find that in the free approximation, the space of boundary local operators is just the exterior algebra of the Lie algebra. And in fact, I should have put in a dual here, shifted by one. Interaction vertex leads to correction coming from a diagram of this type. And this gives me that the BRST operator acting on the space is just the Chevalier-Allenberg differential. And so in summary, this space of morphisms from DD is just the Chevalier-Allenberg cochains. So this underlying vector space is the exterior algebra of the Lie algebra. And the action of the differential, which I call M1, is given by the Chevalier-Allenberg differential. And the product is given by the exterior algebra structure. So I get a differential graded algebra. So the higher maps are 0. So I get a differential algebra, differential graded algebra, special case of an A infinity algebra where M1 and M2 are the only non-zero maps.
Could you say again what M1 and M2 are in this case?
So M1 is just the Chevalier-Allenberg differential.
Okay.
And M2 is given by product of two ghosts, exterior multiplication of two ghosts, C and the antisymmetric product.
You're calling it exterior because they are anti-committed.
Yes,
It's just
exactly. Yes, that's right. So it's just the simple differential graded algebra as the space of local operators on the Dirichlet boundary condition. This was just for a single object. The point of having the category is that there can be more than just a single object. Otherwise, it's just an algebra. So we can take multiple copies of the Dirichlet brane.
Sorry
yes.
to ask again, but
No worry.
I'm lost in the connection between what you just defined and the physics. So we have this theory with the boundary conditions. Namely, we have said that that's the one where B can be anything, right?
It's the other one. So that's sorry for the it's the one where A can be anything at the boundary. Yes.
And then actually you say that A can be gauged away, so if there are no local operators.
Right.
But in this setup, you take seriously the ghosts. And then the gauge invariant local operators are gauge invariant functions of the ghosts. That's the cohomology of the, this is what he called the Chevalier-Allenberg differential.
I see.
But the complex, here they don't just take the cohomology. They consider all the local operators with the BRST operator acting on them and the multiplication and possibly higher order products. Although in this case, there aren't any.
Yes.
So all the local operators without imposing BRST symmetry or any function with the ghosts with the obvious multiplication.
But what are these in the physical? We didn't expect anything in the physical theory.
Well,
Or maybe
the sense in which
we
we don't have anything is that since we don't have any physical operators with negative ghost number, we won't be able to compute any non-zero correlators. So in another situation that wouldn't happen to us. But here, the definitions tell us to allow local operators that depend on the ghosts. And so when we quantize, there are indeed. This would be true in Yang-Mills theory in QCD also. We don't usually talk about it, but in the usual setup, if you ask what are the BRST invariant operators, a local operator that only depends on the ghost C and is gauge invariant is a perfectly good BRST invariant local operator. We don't usually talk about it because since there are no operators with negative ghost number, we can't do anything.
Normally we think of a Hilbert space as being gauge invariant states, and there's a well-defined Hilbert space with gauge invariant states.
Yeah, it seems that Jim didn't actually have a Hilbert space because he had what amounts to an OPE algebra. The MNs means you could multiply any number n of operators, but there wasn't any rule about a correlation function, which would be inner product. So in this setup, there can be, as in QCD, if we were to discuss general gauge invariant local operator, gauge invariant BRST invariant local operators in standard quantization of QCD, we would say that the trace of CQ is wrong. We don't usually talk about it because we can't do anything. But
But normally we would think, I would think of the gauge invariant operators as they don't involve ghosts or anything.
Well, the
Like
general,
this. There are some operators that should be,
well, the reason we usually don't talk about the ones with positive ghost number is that there aren't any of negative ghost number. And therefore, the ones with positive ghost numbers for most physical applications aren't useful. But if you look at any general treatment of BV or Beer's declinization, you'll find that what's proved is that there are no gauge invariant operators with negative ghost number. It's not proved, and in general, for example, in QCD, it's not correct, but there are none with positive ghost number. So here you're hearing about the ones with positive ghost number in this current presentation.
Maybe it's worth commenting that in two-dimensional gravity, quantum gravity operators, but positive goose number may have a physical effect, as we learned in the old matrix models.
let's see, if I just discretize QCD on the lattice and so on, I should be able to talk about local operators. There we don't get any.
No, but if you did Fourier Popov quantization, you could do a lattice version of the RST quantization and so on. You can ask, the procedure you suggested is correct. So you can ask, how come the other procedure that in some sense is also correct, produce these extra operators?
Right.
The answer is that since the extra operators all have positive ghost number, you can't do anything with them for ordinary applications.
But in 2D gravity, you can do something with them. There are backgrounds when we turn on the positive ghost number.
Without getting to G gravity, just discuss string theory. When you integrate over modular space, you actually want a product that has ghost numbers 6G minus 6 plus 2N. So there you can do something with operators with positive ghost number. But in gauge theory normally.
Perhaps it will also be clear when I discuss Koszul duality that this actually does have quite a bit of physical information. So yes. Okay. So now I'm just going to talk about multiple copies of the derivative ring. And so this is given by saying I take a multiplicity space V, whose dimension gives the number of copies we're taking. And the space of local operators for this enhanced boundary condition is given by this tensor product of the Chevalier complex with endomorphisms of the vector space V. And this also has a differential graded algebra structure given by combining matrix multiplication with the DG algebra structure on the Chevalier complex. And we can moreover turn on a boundary interaction. Boundary interaction corresponds to choosing a degree 1 element of this algebra that satisfies the Morse-Cartan equation. And the Morse-Cartan equation, in fact, is for an element of this type, CA times an endomorphism TA, is just the condition that the TAs form a representation of the group of the Lie algebra G. And the turning on a boundary interaction means that I insert this operator into the path integral. So this is nothing but a description of the boundary Wilson line associated to the representation V of G. So in other words, multiple copies of the derivative ring deformed by this boundary vertex is the same thing as a Wilson line.
When you say the boundary interaction, I think what you're doing is
Yes.
you were describing local operators.
Yes.
But there's a descent procedure. So
Exactly.
the local operator is a one-form part.
Yeah.
Which you can regard as a boundary interaction that you add to the action.
Yes, I skipped all that. Yes, thanks. Yes, and that gives me this this thing. Yes, that's exactly right. Yes. So right. So this is just an alternate way of describing Wilson equivalent. And so now I more generally, so I have V and W, and then I want to describe the morphism space of local operators that live at a junction. It's just given by this Chevalier complex times the space of linear maps from V to W. And so this has the structure of a chain complex, where this is the Chevalier-Eilenberg differential acting on the ghosts, and this is the differential induced by this boundary, this Wilson line action acting on the endomorphism from V to W. So this squares to 0, and the product is given by So, okay, so then I also have a composition law. The composition is given by taking the product of ghosts with composition of endomorphisms. And there are no higher products. So that gives me totally complete description of a category. So usually this space, where I tensor product the space of linear maps with the Chevrolet complex and equip it with this differential, is written in homological algebra as the derived morphism space from a representation V to the representation W, R VW. And so we have thus seen that the Dirichlet boundary conditions give us a category, which is the derived category of representations of the algebra G. If I pass to the homotopy category by taking the degree 0 part, by taking the cohomology and degree 0 part of the cohomology, I get the ordinary category representations. But this has less information. And just as a remark, I think this comment that this should be the derived category should also apply to discrete gauge theory. And I'm not really sure if this has been properly discussed. So that was my description of the subcategory Dirichlet boundary conditions. It's the derived category of representation of the group of the algebra. So now we can also talk about Neumann boundary conditions. So now the operator that survives is B, not its derivatives. And now I compute the OPE of two B's given by a diagonal of this type, and it leads to a relation as follows. And so it's the space of B products of B's modulo this relation. So we see that this, and there are no other diagrams that contribute, I think. And so then the morphism space of a Neumann boundary condition to itself is just the universal enveloping algebra. So B's, products of B's, and this is all in degree 0, 1. So this is, all these are what you would consider physical. So the degree 0 operators with B's with this boundary condition. So the morphism space is the universal enveloping algebra. And I can also talk about enhanced versions of Neumann boundary conditions. So we see that there are two kinds of categories, subcategories, those built from Dirichlet boundary conditions, those built from Neumann boundary conditions. And my claim is that I only need to know about one of them. If I know one of them, it secretly knows about the other one. This is a consequence of the fact that the endomorphism space of a Dirichlet brings the Chevrolet complex, and the endomorphism space of Neumann brings, which is the universal enveloping algebra. These are Koszul dual as augmented differential graded algebras. So these branes D and N are what I call Koszul dual boundary conditions. This is a notion in homological algebra, which initially was the observation that the categories of representations of two algebras are equivalent, even though they're different algebras. So essentially one has all the information about the other. And so here we're seeing a very physical sort of realization of this. So we only need to talk about essentially one of them in order to know everything about the other. And so I will return to this notion later in the talk. So this was my description of
What's the case of Dirichlet and Neumann?
Oh, so yeah, those are transverse. I think it's just yes, there's not.
Hom is empty,
I think it's one dimensional.
just in degree 0.
Yes, that's right. So yeah, there is sort of transverse.
Normally we go between one and the other by integrating something.
Yes.
We put something on the right hand side and then integrate. Is that an explicit?
So there's I don't think it's in the literature, but there should be some interface that maps one to the other that you can construct in this theory. Yeah, Koszul duality type interface. I mean, yeah, the physics papers on this concept are very recent. There's a paper by Natalie Paquette and Brian Williams from a couple of years ago. There's papers by Kevin Costello and so on. But it's not widely.
Is Koszul duality something that is explicitly understood? It's not the conjecture duality.
Yeah, it was developed by mathematicians, so it's a precise definition. two Koszul dual algebras
Okay.
have a precise. Yeah.
So you said there's a unique boundary changing operator between Dirichlet and Neumann, right?
Well, I haven't really described it here, but what I was saying is that there is an interface. I haven't constructed it explicitly that should map.
But since it is one dimensional, so there's one of them
Uh,
up to a C number.
Well, what the question means is, on one side of the interface, A is zero, the other side B is zero. So what can you insert
mhm,
at the endpoints?
mhm.
So the space of things that you could insert there, I thought you said is one dimensional, right?
Yes.
Well, what that means is there's nothing you can change. There's the identity.
Identity.
Yes.
Curly B is zero on one side, curly A is zero on the other side. So where they meet, everything is, I think, is probably. Also has one.
My question is, if you take one of these interface and it's inverse, and you take their OPE,
Mhm.
you get identity, what you get? You should get just one in DV or NN.
So okay, interface I haven't really studied carefully in this theory, so I can't answer on the fly. But I think it's the kind of question that I could probably answer carefully, thinking about it. Yeah. Okay, so yeah, so this was just an illustration that this even in the simple theory there you can have nice stuff. But now I will turn to the almost halfway to the review part of the talk now, which is review of the algebra of infrared. So what I described so far was just the category of boundary conditions for a perturbative quantum field theory. Now I will switch to an example of a totally different nature, different flavor. That's the main focus of the talk. So here we will consider a two-dimensional quantum field theory with n equals 2 supersymmetry. And that's actually the smallest SUSY or have a topological twist, topological boundary conditions. Suppose that the theory is massive and has an unbroken U1R symmetry. And so this algebra of the infrared refers to a construction of the category of supersymmetric boundary conditions for this 2-2 QFT from the low energy effective degree theory. So you construct the analog of this category that I constructed for the BF theory, except you do it using the vacua, central charges, soliton spectrum, and interaction vertices of these solitons. So this collectively I will call infrared data. So it's a lot of stuff, but I will describe it one by one. So the infrared data of low energy effective field theory, the infrared data, which is the data of the low energy effective field theory for two-dimensional QFT, consists of a finite set V of vacua, where an element is written as follows. And for each number, each vacua, you have a complex number. And the physical information in these complex numbers is that the central charge in the supersymmetry algebra in the IJ soliton sector is given as a difference of these vacuum weights. And I will assume that these numbers in the complex plane are in general position. And because I have a Hilbert space with a central charge and soliton sectors, I can consider BPS saturated states. And I will let Rij be the Hilbert space of Ij BPS particles. These are the states that saturate this BPS bound. So what I'm saying so far is that given the theory, I have a set of vacua, a set of vacuum weights, and a collection of Hilbert spaces Rij for each pair of vacua, each pair of distinct vacua. And these will be again graded, not by the ghost number now, but by the U1 fermion degree, which actually is ghost number in the twisted theory. I will talk more about these later in Landau-Ginzburg theories. And because of CP, there's a pairing between IJ and JI solitons. And so I said that I have vacua, central charges, spaces of BPS particles. But then I also said I have interaction vertices of BPS particles. And describing this, so these are the analogs in the 2D BF theory of the structure constants FABC that appeared in the interacting part of the action. So these will be things that couple BPS solitons. But describing it more precisely takes some work. So I will do that work now. So in order to describe the interaction vertex, I first have to describe the notion of a cyclic fan of solitons. So this consists of a collection of vacua ordered so that they lie on a circle. So the condition on these vacua is that the central charges are points, clockwise ordered points on a circle. So the arguments are clockwise ordered points on a circle. So here I have a cyclic fan of vacua of 5 vacua. And so Zij, the phase of Zij is to the left of the phase of Zjk and so on. And to such a cyclic fan, I will assign the cyclic tensor product, soliton spaces. So here I would assign Rij, Rjk, Rkl, Rk, Rfi. And I sum over all these things to form a space I call Rc. And so just like the A infinity category before, which is an open string concept, RC you should really think of as a closed string concept. And as familiar from old work of Zwiebach, closed string sectors usually have L infinity algebras associated to them. And so this space carries the structure of an L infinity algebra. And L infinity algebra has a collection of maps lambda 1, which is a differential again, think of it as a BRST operator, lambda 2 is Lie bracket, except it only satisfies the Jacobi identity up to lambda 1 exact terms, and so on. And the specific way these maps are built uses the diagrammatic formalism of webs. So this is a notion described in great detail in this Gaiotto-Moore-Witten paper. And so this is simply a graph drawn on the plane where the faces are labeled by vacua and the edges satisfy the slope constraint. And the slope constraint states that an edge separating faces labeled I and j must be parallel to the complex number, which you don't see here, Zij. And so this is some random web. It just means that I have some spaces are labeled by vacua, and this edge right here is parallel to the central charge Zij. This edge here is parallel to the central charge ZML, and so on. So this, given vacuum weights, I can form a collection of webs. And these come in moduli spaces. And it's called taut if the only modulus of a web consists of the translations of vertices and scaling, like overall scaling of the whole picture. So this example is not a taut web because I can scale this and scale this triangle independently. But if there were just one modulus, I would call it taut. And so to each web, there's a linear map I can assign on this space of cyclic fans by applying this contraction map to each internal edge. And lambda n, the nth L infinity map is given by summing over taut webs with n vertices. And one can prove that this satisfies the L infinity relations by looking at moduli spaces of webs with more than one dimension compared to a taut web. And it's a Morse theoretic kind of argument. And it's important here to assume that the vacuum weights are in general position. Otherwise, these properties of webs would break down. Okay, so my goal is to describe vertices, interaction vertices. And so first of all, the interaction vertex is simply an element carrying degree 2. And the component of beta lying in this kind of summand is meant to capture an n+1 valent vertex of solitons that are involved in the fan. Just like FABC in the 2D BF theory is meant to capture vertex that couples BAA in the BF theory. But it can't just be any random element. It's required to give a consistent supersymmetric theory, so it has to be compatible it has to give a nilpotent supercharge. And so that corresponds to the fact that it's required to satisfy this Morse-Cartan equation. This Morse-Cartan equation is analogous to the fact that any random structure constants, F, A, B, C, won't define a consistent two-case theory, but if it satisfies the Jacobi identity, then we would get a closed VRST operator, and it would be a consistent gauge theory. And in fact, the Jacobi identity can in fact even be viewed as a Morse-Cartan equation in the Lie algebra for an element of the Lie algebra of polyvector fields on the dual Lie algebra. So what I'm saying here is that I've described a condition for a consistent set of interaction vertices of solitons. And so in pictures, we should just think of it as follows. So beta is given by a sum of bivalent vertices. So this is a coupling that couples one soliton phi ij with another soliton phi ji, and this is weighed by a strength n. You have trivalent vertices that couple three solitons weighed by the strength n, this n, and then you have higher order quartic, quintic vertices and so on, depending on the different families that are available in your theory. So this is a crucial part of the infrared data. And to summarize, the infrared data of a massive quantum field theory consists of a vacuum set, central charges, soliton spaces, and this Morse-Cartan element beta. So in other words, if I hand you 2,2 massive quantum field theory of a certain type, then it should allow you to so the low energy effective field theory should somehow be formulated just in terms of these basic pieces of information.
What exactly is beta in the, I mean, I think I understood the previous ones. Is there a more physical way of saying what beta is?
Well, I mean, beta is, as I said, is some kind of, I will describe an example, but it's a coupling of solitons. So it's
vertex probability amplitude, that's all it does.
yeah, roughly. I mean, so I'll describe more precisely what it is in the Landau-Ginzburg model. Yeah, so.
I mean, I found it confusing that it is a sum over many different things.
Well, yeah, so I mean, a vertex can have trivalent lambda to, phi to the fourth, phi cubed, phi.
I see.
Yeah.
Okay.
In general, this is it involves all vertices of all the elements.
Yeah, like a complex number associated to the three-valent vertex.
Yeah. So this in fact, it's going to be an integer, but in general, yeah, it's going to be some number. So this n is a number associated to this vertex. This is associated to this vertex, and so on. So those are the numbers. Yes.
So the first one is just the inner product of just one. It's not one number.
No, not necessarily. It could be anything. As long as it could be anything that solves this.
Well, all these things are computed by solving
Yes.
supersymmetric equations, right?
Yes.
They describe it.
Yes.
So integers are going to be the number of solutions that are based on boundary conditions.
Yes.
That are consistent with these pictures.
Yes.
Oh, I see. So this first 10 is like the degeneracy of the soliton, like how many solitons there are.
Is that right?
So it's gonna be, this n is gonna be the number of it's gonna be the number of solutions of the instanton equation with this kind of so it's the number of interpolations between two solitons. So on a plane, I can define if I have a given soliton in the past, a given soliton in the future.
So IJ are specific to them.
Yes. And so it's going to be the number of supersymmetric configurations. So
I see. So, but isn't this the same as saying what the number of ground states of the solitons is?
It actually isn't one because there can be classical ground states that are more than the quantum ground states. Quantum corrections to the soliton spectrum.
Mhm.
Is that right?
yes.
So, although not often discussed, there's a two-dimensional instanton-like equation that describes transitions between different solitons.
Yeah, so I will describe that in short.
That's what this first one is supposed to be.
The first one is supposed to be a picture like this, and so yeah, so the second one is, well, it's all in the pictures. The second one is supposed to be, I solved the solution, I solved a certain equation with these junction type on. So you think of it as a junction of
I think
solids.
this will be clearer when you do the
Yes.
Ginzburg
Yes.
model. And it's
Let me see
a little
if I-
too abstract right now. So
Yeah.
if you do the Landau-Ginzburg model, it'll be lots.
Let me understand first the first one. So,
Okay.
so we have some solitons and we take all quantum effects, right?
Mhm.
Just the IJ soliton, all the quantum effects, there would be some degeneracy.
In general, by the way, these are two different solitons.
Degeneracy is different from the classical degeneracy in general. And the dot is an instanton that lifts some of the classical solvents.
Ah, I see. So this relies on some, you're doing some approximation.
Well, you were doing some approximation, we talked about solitons, I think you meant classical solutions.
Well, the soliton is a particle in the theory.
Yes.
There's some degeneracy.
Kant defined Rij as a space of BPS particles, which I think is slightly inaccurate. Even classically or quantum.
It doesn't matter. I mean, in general, there will be some biluminescent vertex. I don't care.
I think of them as nearly BPS particles, which the instantons are going to lift to give us the exact BPS particles, which is cohomology of Rij.
Right, I think that the confusion here is that the fact that the classical solitons are sometimes lifted isn't well known.
Okay.
And the red dot represents an instanton that might have lifted some of the passive BPS solutions.
So yeah, hopefully this will be clear when I talk about. Yeah, in general, this is counting you know, sort of domain wall junctions. That's that helps. And this is just, you know, a junction involving two solitons. And so okay, yeah, so to get more concrete, I can define a quantum field theory given by a superpotential W, and it's given by a sum of a Kähler potential and a superpotential W. And we suppose that W is Morse in the sense that it's isolated, it has isolated finitely many critical points, and the Hessian at each second derivative matrix at each critical point is non-degenerate. Then the vacuum set is given by the critical points of W, and the vacuum weights are given by the critical values up to an overall phase, which I choose. And then I can compute that the central charge in the Susi algebra is given by a difference of vacuum weights, difference of critical values. And the space Rij of Ij BPS solitons is obtained by quantizing a classical soliton. So classical soliton is a solution of this first order equation, which we obtain from applying the BPS trick. And we choose zeta to be the specific phase for any chance to have a non-trivial solution with Ij boundary conditions. And so really this quantization leads to a pair of states because there's a fermion, because there are fermionic zero modes, superpartners of this translational mode of the soliton. And Rij by definition is the space of states obtained in the upper fermion number. So I described the first three things. This is critical points, critical values. These are solution spaces obtained by quantizing classical BPS solitons. The third point, or the final point, the interior amplitude, is actually given by solving the 1/4 supersymmetric equation of this theory, which is the zeta instanton equation. Simply take this equation and replace x by z bar with fan boundary conditions.
So that's an equation for a configuration that preserves one of the four supersymmetrics.
Yes.
While the soliton equation had preserved two.
Two, yes. That's right. And so there are, yeah, so the point is we have a boundary, you want to specify, you want to count solutions with the boundary conditions that satisfy this kind of boundary conditions that are captured by this kind of picture. This means the following. It means that if I go along infinity, along one of this sector, go to infinity, and the solution approaches a vacuum phi I naught, If I go in this sector, the solution approaches vacuum phi I naught, but if I go along this specific ray, I actually obtain a soliton. In the W plane, if I take a projection of this such a map in the W plane, then it's actually conjectured to fill in the entire triangle in a one-to-one. Not a triangle, polygon, this one. So you're looking at this kind of solutions, counting rigid solutions, and for each such boundary condition. So once I specify which solitons I have at each edge, I have a well-defined number n.
Is the action related to the area of this, right? This letter or this?
I actually, okay, so I actually thought that this was true, but then I remember checking that it wasn't. So, yeah, well, I mean, in general, this doesn't have a finite action because stuff is non-trivial stuff is happening.
Then there's a natural regularization.
Yeah, but there's a regularization, and I don't actually know if this is the area. It would be nice. I don't. It's certainly true that the mass of a VPS particle is this length. So, yeah. So, okay, so that's the general end. So now, for the quartic Landau-Ginzburg model, let me be even more specific now. I have 3 vacua, 1, 2, 3, located at the roots of unity with these critical values and these central charges. And I can show that between each pair of vacua, there is a unique soliton trajectory. And these are the fermion numbers. We have these fractions because there is charge fractionalization, solitons in 2 dimensions. And so by Z3 symmetry, these 3 spaces are all 1-dimensional, and the fermion number of the state is 2/3, because remember I took the upper fermion degree. And then the anti-solitons are also 1-dimensional with this fermion degree. So those are the central charges, vacua and soliton spaces. And so by a conjectured analog of the Riemann mapping theorem, we also have a trivalent vertex. So, you know, the Riemann mapping theorem says that I can basically fill in any shape, map it in a holomorphic way. And so there should be some version of that for not holomorphic maps, but for the zeta instanton equation. And if such a thing is true, then we can actually conclude that there is a non-trivial interaction vertex. Or we could just use some numerics to show that there is a non-trivial solution with these fan boundary conditions in the theory. So we have this coupling of these 3 solitons. So the central charges look like this, and the coupling, the trivalent coupling of these solitons is represented by a picture like this. And this trivially satisfies the Morse-Cartan equation because there's in this example there's nothing in degree 3. So we finish specifying the infrared data of this model.
So there are no, for example, 4 solitons.
Yeah. No couplings like that. Yes. And so, now remember our goal in this talk is to talk about a infinity category of boundary conditions. So now, using this basic infrared data, I claim that there is a description of the category of boundary conditions for this massive Landau-Ginzburg model. And this involves generalizing fans to half-plane fans. This is self-explanatory. And webs to half-plane webs. So we choose a half plane, and the objects in our category are now thimble boundary condition for each, quote unquote, thimble boundary condition for each vacuum I and V. So you have as many objects as vacua. And if the objects, actually come with a certain ordering, I is less than J if the central charge lies in H. And so the morphism space between Tj and Ti is given by summing over all half fans of this type. So we sum over fans to get R hat Ij, the morphism space from Tj to Ti. I sum over all half fans that start at I and end at J, and assign the corresponding soliton spaces. That's my definition of the morphism space. R hat II is C, and so this has a sort of semi-orthogonal decomposition structure, where the non-trivial formal matrix and the non-trivial morphism spaces are all here. These are all trivial. Oh. And so the k-day infinity map on this category is obtained by summing over taut half-plane webs with k boundary vertices. And in the bulk, for the bulk vertices, you use the interaction vertex. So it's very similar to traditional perturbative quantum field theory, where you have a diagrammatic rule with some vertex and some propagators, roughly. And so let me now describe this in the quantic Landau-Ginzburg model again. So because I had this particular central charge configuration, the vacua are ordered in this way. And there's only one fan for each space, for each pair. And so each morphism space, just like the soliton space, is one-dimensional. And in order to describe the non-trivial multiplication map, we have to look at taut half-plane webs using the bulk interaction vertex. So remember that I had this interaction vertex for the quantic Landau-Ginzburg model. And these are the three these are the three central charges. Using this interaction vertex, I can form this taut half-plane web. And this gives rise to a non-trivial multiplication. It says that the multiplication of the state of the local operator in 1, 2 with 2, 3 is the local operator in 1, 3. If I take the full category generated by these three basic thimble objects, this turns out to be the representation category of the A3 quiver. And I can verify that this is the same answer produced from the more traditional prescription used in Fukaya Seidel categories. So if you're familiar with the subject, in traditional Fukaya Seidel categories, objects of the category boundary conditions consist of Lagrangian submanifolds. Morphisms are intersection points, and A and maps are given by counting holomorphic disks with Lagrangian boundary conditions. So what someone like what mathematicians who study this field would draw is that they would draw these three thimbles and rotate them slightly and show that they intersect. They have one intersection, pairwise intersection point, and a holomorphic triangle. And all this together would reproduce exactly the same things. One-dimensional spaces with this non-trivial multiplication map. So the web way of doing things and the more sort of geometric, using actual Lagrangian submanifold way of doing things agrees. So we see that, therefore see that, and you can actually show that, and this is true in general. So we therefore see that the algebra infrared gives us a web-based formalism to construct the category of boundary conditions for massive Landau-Ginzburg models. Gives us an alternate viewpoint on the difficult subject of Fukaya Seidel categories. And it allows for a more, it also refined, I haven't discussed this, but it also allows for a more refined understanding of wall crossing phenomena. So it leads to things like categorification of the Chikadi-Vafa wall crossing formula, and also categorification of this classic mathematical subject known as Picard-Lefschetz theory and Stokes matrices. And mathematicians have also built upon this work. Kapranov, Kontsevich, Soibelman reformulated Gaiotto-Moore-Witten using secondary polytopes. And Kapranov, Soibelman, and Sukhanov further built upon it by introducing the notion of a perverse chauffeur. And I have no idea what that is, but at some point I'll read this paper. That was my review of the standard story of the algebra infrared. And in the remaining time, I will talk about the generalizations twisted messes. So any questions so far? This was very quick, I'm sorry.
This product is the same as the stability of the operators.
Yes. That's what it's meant to capture. Yes. I mean, there's this web-based algorithm to compute it, but at the end of the day, it's meant to capture the product of local operators at a junction.
But maybe it's worth saying that there, the information is it's not just in the product of two operators colliding, which is what we usually think of as the OPE, but they're sort of nth order products. N operators, I think of them as simultaneously colliding.
Mm-hmm.
That's what the MNs are.
Yes.
That's more information, and then they satisfy some quadratic relation called the A infinity relation.
So you cannot get the N1 from.
No.
No, they're
No,
independent.
No, see, that's, the usual idea is, okay, you just take the OPE of two operators and you're done. But there are these MNs,
Yes, not necessarily.
which you do not construct out of the M2s.
Yeah, so.
And they measure the failure of associativity.
Yeah, so there will be, independent diagrams, so M2 would be given by a diagram like this, one I just had, M3 would be given by some diagram of this type. So there are three now boundary vertices, so.
So I can't construct that out of M2.
Yeah, right. Okay, so this final part is a work in progress with Greg. It's been going on for a while, but hopefully we're coming to completion. And so the point here is that now I want to, so this beautiful idea, the algebra of the infrared, should apply more generally. So the point is, a general supersymmetric signal model with a Kähler target space admits more kinds of potentials. It's not just, so superpotential is not the only thing I can turn on. And in fact, even in the superpotential world, there's a generalization, which I'll discuss later. But one thing I can do is if my Kähler manifold X has some abelian group of isometries, continuous isometries, I can turn on twisted masses for these isometries, which corresponds to adding a potential given by the square of the moment map. And this gives a massive sigma model, assuming that the fixed points of the isometry are isolated and non-degenerate. And you have a central charge, non-zero central charge, given by the twisted mass m times the charge corresponding to the abelian symmetry, and a difference of the moment maps at the infinite ends of space. This is the classical central charge. Letting I equals j in the formula, we see that zii does not necessarily vanish. So zii is just, instead there can be massive excitations in a particular vacuum that are charged under the abelian A that are BPS. This was not allowed before. Before I wrote zij equals to zj minus zi, so zii equals 0. And so such particles are not covered by the web formalism. And I can still ask the same question, however, that if I have such a theory, how do I describe the category of boundary conditions? And the algebra of the infrared won't answer that. So how would I construct such a thing? And there's a canonical and well-studied example. If I take the CP1 model with a twisted mass for the rotations about the z-axis, thinking of this as a sphere, then indeed I can have non-trivial BPS particles coming from excitations about the north and south pole. In addition, I also have this weak coupling BPS spectrum, similar to the BPS spectrum of Seiberg-Witten theory, consisting of tower obtained by quantizing a basic particle, and it's sort of so there's an integer, it's a sort of dionic excitations in 2D context. And for example, if I'm given this theory, how would I recover the categoric boundary conditions from these BPS particles? That's the kind of question I want to ask. How much time do I have? Can I finish in 10 minutes?
Yeah.
Okay, thanks. And then the other kind of thing that's not covered in the previous algebra of infrared is, so we observe that in order to define a Landau-Ginzburg model, we don't actually need a globally well-defined holomorphic function W. All we need is its well-defined first derivative, theta. So in order to define a supersymmetric 2,2 field theory, the data is actually just a closed homomorphic one form. That's the right data. And the general formula for the central charge in this more general setting is that it's just given by integrating the one form along the path of the trajectory. And so if alpha is exact on X, this can be converted to a boundary integral, giving us the expression zj minus zi before. However, if the first Betti number of the target manifold is non-trivial, then alpha can be cohomologically non-trivial and it can have a non-trivial period. And in such a case, we may no longer convert it to a boundary integral. And it still gives a massive theory if the zeros of alpha are isolated and non-degenerate. However, the assumptions on the central charges break down. So in the II sector, a non-trivial, if a path wraps a non-trivial one cycle, we no longer have zi equals 0. Instead, it's given by the period integral. And so conditions of the web formalism don't hold. And more dramatically, I can even have BPS solitons that go to the same 0 phi I at both infinites of R. As long as it satisfies this equation, which is the analog of the flow equation in the more general case. So this is still a BPS particle with mass given by the absolute value of the period. And we call such things closed solitons. And so the question in this context is, how do the interaction vertices of such closed solitons formulated, and how do these such closed solitons enter the calculation of the category of boundary conditions? And so this is kind of a Novikov analog of Picard-Lefschetz theory, where Novikov usually means we generalize functions to one forms. And so this is the version we will keep in mind. And so a familiar trick from Novikov theory is that we just work past to a suitable covering space. So instead of working on X, we pass to a covering space X twiddle, such that pullback of the one form becomes exact. And then we can work with the holomorphic function globally defined on the covering space X twiddle. Then this will have some deck group, and we will work equivariantly with respect to the deck group. So that's a standard trick familiar from Novikov theory. And indeed, this is an important step. So if I let gamma be the first homology modulo the kernel of the central charge homomorphism, I can consider a covering space by quotienting the universal abelian cover with the kernel of Z. And this will have deck group gamma, which is a free abelian group of rank R. And we can then work globally well-defined superpotential W twiddle on this space X twiddle. Then for each critical point, we have a gamma torsor of critical points on X twiddle. And so at the very least, we'll have to allow for a formalism that allows infinitely many vacua. But all these vacua will have well-defined critical values at least. And moreover, the soliton spectrum on this covering space will be such that it's invariant under the shift symmetry. So the soliton space between A and B is the same isomorphic to the soliton space between shifted versions of A and B. You shift them simultaneously. But there's a more serious issue which prevents such a thing from naively working, which is that if you have such a shift property, then for a particular element gamma, all the critical values are actually aligned. They all lie along common lines. So there are infinitely many critical values that lie along a particular ray. And previously, we didn't even allow for 3 values to be aligned. And here there are infinitely many aligned values. And so this leads to a highly degenerate situation for webs. And we need a systematic way to get around this issue. And what we'll do is we'll try to perturb the superpotential W twiddle in such a way that the perturbed soliton spectrum. So first of all, it breaks its this kind of thing gets perturbed to a non-degenerate thing. And the perturbed soliton spectrum, however, we still want to respect the deck symmetry. And so if this is possible, we can try to analyze the web formalism with perturbed model and then show invariants that are the chosen perturbation. So in summary, we will try to employ the following strategy to generalize to twisted masses. So step 1 would be to pass to a covering space with deck transformation gamma. Step 2 will be to perturb the superpotential W twiddle. And this perturbation doesn't have to be universally chosen. It can be chosen for a particular calculation. Then we'll run the web formalism for the perturbed central charges and perturbed soliton spaces. It gives an A infinity category of the action of that group gamma by autofunctors. Finally, we'll pass to co-invariance with respect to the deck group. So that's our strategy. And in the remaining couple of minutes, I will show how this strategy works for the simplest example. So the simplest theory with a non-trivial period consists of target space being C star and one form being 1 over 5, m over 5 minus 1, perfect complex number m not equal to 0. And there's a single Morse critical point located at m. And in fact, the model has a unique trajectory that wraps the non-trivial one cycle once with central charge 2 pi I m. This is a trajectory that satisfies the flow equation I wrote previously. And so the one form indeed has a non-trivial period for non-zero mass, non-zero m. And so the covering space is then simply the universal cover of C star, which is the complex plane C, where the covering map is the exponential map. And so the superpotential on C is just given by my minus e to the y. So here we have infinitely many critical points labeled by the integers and infinitely many critical values, which are all parallel to the line IM in the complex W dual plane. And the path, the unique soliton path, gets lifted to a path that connects vacuum yk and yk plus 1 that are shifted by units of 2 pi I. So this is a bad situation. We would like to perturb this. Convenient perturbation perturbs this to some kind of convex shape. So this is a non-degenerate case, which is good. And let's see how we can do that. So for a given positive epsilon, we can define W epsilon to be this perturbed superpotential. And then to first order an epsilon, I can show that the critical values have this configuration. And so the image above is actually accurate. So the imaginary, they're shifted from the imaginary axis by a quadratic function. But there's a subtlety, which is that this perturbation can't be considered globally small. If y is large and negative, then the perturbation actually dominates the superpotential. But it doesn't really cause trouble because we can choose epsilon so that it can be considered small for the purposes of a given calculation. Epsilon doesn't have to be chosen universally. And so now I have to compute the perturbed soliton spectrum. And that can be done by looking at the intersection pattern of the unperturbed Lefschetz thimbles because of this property. So in the perturbed theory, the intersection points of thimbles are actually homotopic to the solitons. So I can just look at the intersection of unperturbed thimbles. And there they have this pattern. So these are your Lefschetz thimbles for this theory. And they intersect. Any pair of them actually intersect in this way, because if you go far out enough, there will be non-trivial intersection. And so what you conclude is that for the perturbed model, you have a soliton between any pair of vacua that are arbitrary many units away. And some of them can be depicted as follows. This is a version of the original soliton. This is a version of a soliton that's 2 units away. This is a soliton that's 3 units away. And you see that in the epsilon goes to 0 limit, these actually just trace out a sequence of broken paths of the original soliton. So it's kind of a Fock space of closed solitons. And moreover, you need a perturbed interaction vertex. And my claim is for every triple, there is one, because such a shape can be formed. So this is an example with KLM is 2, 0, minus 1. But in general, it can show that it's there for every triple. And so finally, we have the perturbed IR data consisting of this soliton spectrum, RKL, and non-trivial interaction vertex. And we're finally in a position to compute the category boundary conditions. So for the left half plane, we have this thing. This is the only non-trivial web. There is a one-dimensional space, and if we pass to covariance, we actually find just the symmetric sort of polynomial algebra in one variable as the boundary algebra. If I do the same thing for right branes, the calculation is more involved. I have this kind of webs. There are lots of fans. This leads to a product. This leads to a differential. And these, I don't have a lot of time to explain this, but these diagrams are actually conspiring to reproduce the Kobar complex, which is the well-known construction of the Koszul dual. So I have this huge algebra, but if I take the cohomology, it dramatically simplifies to just the exterior algebra. So in other words, the left boundary conditions is this symmetric algebra in one variable. The right algebra is the exterior algebra, quasi-isomorphic to the exterior algebra in one variable. So we have thus reproduced the symmetric exterior Koszul duality very explicitly using solitons, zeta instantons, and webs. And so this example, in fact, generalizes. The general statement is that if I have a Landau-Ginzburg one form with a single zero and a single period, we may perturb things, except we now have a generic soliton space and generic interior amplitudes. For such generic soliton spaces and generic vertices, we can still show that the left and right boundary web algebra are Koszul dual. So left and right thimbles, in other words, the left and right thimbles located at the unique zero of alpha are Koszul dual boundary conditions, just like the Dirichlet-Neumann boundary conditions for the 2D BF theory. This is related to mirror symmetry. And we therefore see that the generalization of Picard-Lefschetz theory, Picard-Lefschetz-Novikov theory is intimately tied with the notion of Koszul duality and homological algebra. So to conclude,
So do different deformations give you the same answer? Like your positive epsilon and negative epsilon give you the same answer? Or?
it does that. It's true that they give you the same answer, but the way it does that is actually very interesting. So you get, so the final answer is the same, but the calculation looks completely different. But great question, yeah. So to conclude, so this was just one of the simplest new phenomena that occur when we generalize the algebra Niferet to include theories of twisted masses. In other words, you can see Koszul duality. There's a lot more one can do. You can study examples of many vacuola such as the CP1 model, and in fact, we've done this. We can categorify the wall crossing formula that controls the jumping behavior from the BPS spectrum from a weakly coupled region to a strongly coupled region. We can study bulk local operators and the bulk boundary map in more detail. Construct wall crossing and other kinds of interfaces. And it would be really nice to apply it to the Chern-Simon superpotential and somehow recover A infinity algebras as not invariants. And so sorry for going over time, and thanks a lot for your attention.
Can you describe theories that have both Carroll superpotentials and twisted superpotentials?
Oh yeah, so that is actually a little more tricky because it would require even going beyond this, because there you break all U1 symmetries. So you would expect there is some version of the algebra in the bread, but it'll be more complicated. It won't have any Z gradings. So I don't know how to do that. And in fact, that situation shows up very naturally in hyperkähler geometry, where you can n equals 4 preserving potentials are actually, from the n equals 2 perspective, both involve both superpotentials. But yeah, I don't know how to do that.
Any other question? Okay, if not, let's thank Ahsan again.